In today's video, we're going to look at something seemingly unrelated to what we talked about in our last video. Last video was all about antiderivatives, and now we're going to suddenly change to area under the curve. So what do I mean by that? To help us understand what we're going to be talking about today, let's look at a specific situation. Let's say I finally get the scooter of my dreams, and I go take it out for a spin out on the 7, just that southern parkway at the south of St. George over by the airport. And let's say I'm going a constant 20 miles an hour. I'll have a lot of cars mad at me because that's way slower than the speed limit, but that's about as fast as my scooter can go. So I'm driving a constant 20 miles an hour, and I'm just cruising. Let's say I drive for 4 hours. What's my total distance? How far have I gone? Well, this is simple enough to calculate. It's just 20 times 4. The reason why is because we're going 20 miles every 1 hour, and I'm going for 4 hours. And so I'm left with 80 miles. Okay? So I would have driven 80 miles. But what's actually happening here graphically? If I were to graph this situation, if I were to graph my velocity, well, like I said before, I'm just going a constant 20 miles an hour, which means if I were to graph it, all it is just this horizontal line there at 20. Okay. Well, if I look at my x-axis, what does my x-axis represent? My x-axis represents time. How many hours I'm actually out on the road. Right? And we can see that it doesn't matter how long I've been out there, I'm still going 20 miles an hour, right? I'm always driving 20 miles an hour. That's the whole point of it being a constant value. Okay? But how does this relate to the total distance I've gone? Well, take a look at this rectangle right here. Oh, sorry, let me use red for this. Take a look at this rectangle. This rectangle has a height of 20 miles an hour, or 20, and a width of 1, which means the area of this rectangle is 20. Well, what does that area represent in terms of my situation? How far have I actually gone after 1 hour? If I'm going 20 miles an hour, I should have gone 20 miles. Well, let's expand this rectangle. Let's make it a little bit bigger. Okay? Let's expand this rectangle to the 2. This rectangle still has a height of 20, but now has a width of 2, right? Because 1, 2. What's my area? My area under my function is now 40. What does it represent? It represents the total distance I've traveled after 2 hours. So if I skip to the end, right? If I calculate the area under my graph from 0 to 4, this is a width of 4 hours, a height of 20, and so the area is just the area of this rectangle, and I get 80. So it turns out that the area under the curve can be a significant value. In some cases, that value would be important to calculate. In this case, it's useful to calculate because that area under the curve represents, and I'm going to specify this because this is my velocity curve. The area under the velocity curve represents total distance traveled over the course of those 4 hours. So, because of this now becomes a valid branch of mathematics. Can I somehow calculate the area under the curve? Well, it turns out if you have a constant function, it's really easy, right? Because what shape did it create if I just had this constant function? it creates a rectangle. So for a constant function, finding the area under the curve is as simple as just finding the area of a rectangle. Okay, in fact, and so that's what happened for us. Because my function was just this constant function. In fact, if I wrote this velocity function out, my velocity function didn't depend on time. It was always just 20. If I were to actually notate the math that I've done, if I were to use correct notation for this, to calculate the area under the curve, we actually use the same symbol that we used in 4.1. So in our case, what we just did is we took the area under the curve for our function. Our curve in this case, though, was just this constant velocity function. And we evaluated it from 0 hours to 4 hours. So what's new here is that I now have numbers next to that very skinny s. And those numbers represent your bounds. Where are you finding this area under the curve? From where to where? And in our case, we were looking from 0 hours to 4 hours. And what did we figure out? That this was just 20 times 4, which was equal to 80. And that's because it's just the area ended up just being a rectangular shape, and so I have a formula for a rectangular shape. Well, let's look at another example. Let's look at the area from 1 to 2 of the function 1/2 x. I'm going to take away the application here, and we're just going to look at this purely mathematically. So what does this mean? This means I want to calculate the area under the function 1/2 x from 1 to 2. Now I want to point something out. When I'm talking area under the curve, you'll notice that I didn't go from my curve all the way down to negative infinity, right? I didn't go all the way down to negative infinity. Where did I stop? I stopped at the x-axis. So when I say under the curve, I'm really saying what would be more accurate is for me to say between your function, between your curve, and the x-axis. That's what I mean by the area under the curve. It's just between your curve and the x-axis. So this problem's asking me to calculate the area between my function and the x-axis from 1 to 2. Well, let's draw a picture of this and see what I get. Okay. So I know I'm going from 1 to 2, so those are going to be important x values here. If I were to graph 1/2 x, I get something like this, right? It starts at 0. My y-intercept is 0, so I'm starting there at 0. And because my slope is 1 over 2, I'm going up 1 over 2. So what area am I calculating? I'm calculating this area. Well, this isn't a rectangle, so it's not going to be as simple as just doing base times height, right? Length times width. It's not going to be that simple. But this is a trapezoid. Well, I can actually think of it two different ways. I can think of it as a trapezoid, or I can think of this as just a rectangle and a triangle put together. Regardless, this shape is geometric. It's a nice, simple geometric shape that I have area formulas for. So let's break this up into a rectangle and a triangle. So let's first look at this rectangle. So I've got this bottom rectangle. What's the area of this rectangle? Well, the width is 1. What's my height? What's this distance? Since 1 is directly in between 1 and 2, this distance is 1/2. That means the area of this rectangle is 1/2 times 1, which is just 1/2. So the area of that rectangle is 1/2. Now, what about my triangle? Okay. Just to remind you, I have a formula for the area of a triangle. The area of a triangle is 1/2 times base times height. What's my base? My base is still 1. And my height is similar to my height of my rectangle. This was 1/2, so this is also 1/2. So there's my height. So my area for my triangle is 1/2 times 1 times another 1/2, and I get 1/4. So the area of this rectangle, this triangle is 1/4. Therefore, my total area when I put all this together is 1/2 plus 1/4, which is equal to 3/4. Very nice. So, as long as I have simple geometric shapes, calculating the area under the curve isn't too complicated. It's fairly simple. And these simple geometric shapes, notice what did I have in common with these two examples to start out with? Both of my functions were linear, were straight lines, right? My first function was constant, which it was just a horizontal line. And my second function was linear, which means it was just a straight line. So if my function's ever a straight line, then the area under the curve is going to be a nice, simple geometric shape. But what if it's not? Okay, so now let's look at a function that's not linear. So that's not a straight line. So here we have some function f of x. I'm keeping it arbitrary, but we're assuming that it's not necessarily a straight line. And I'm taking and I'm trying to find the area under the curve between A and B. So A is my starting point, B is my ending point. That means I'm trying to solve for this area. Now, is that a nice geometric shape that I know the formula for? Absolutely not. I don't have a nice formula for this, so I can't just calculate it straight out. It's impossible. Anytime I have any sort of a curve, this is impossible. I can't just calculate it using a geometric formula. So the best thing we can do as of now is just to estimate this. That's the best I can do, is just to estimate what this area is. Okay? Well, the most simple way to estimate is just to turn this shape into a rectangle somehow. Okay? Well, the width of this rectangle is easy enough. I'm just going to use this width. What's this width? Well, it represents the distance between A and B, which you can calculate using subtraction. So this is just B minus A. Well, what do I use for the height of my rectangle? Well, I have a couple of different options. You can either use, I don't want to pick some point down here, right? It makes the most sense for me to pick one of my corresponding output values. So I can either pick this as my height. I can stop there as my height, and this represents the corresponding output value for A. Or I could use this point, which is the corresponding output value for B. In our case, let's go ahead and use this point. So if I use that as my height, then that gives me this rectangle, and then I can estimate my area by simply doing f of A, representing the height of my rectangle, times B minus A, which represents the width of my rectangle, or the base of my rectangle. But that's really not going to be the most accurate estimation. How could I make this more accurate? Well, it turns out to make this more accurate, I should not have shaded this in because now I've erased it all, but to make this more accurate, I don't have to limit myself to only one rectangle. Sure, one rectangle makes my computation a lot quicker, but if I'm going for more accuracy, what I can do is I can make multiple rectangles. So let's say I want to break this area up into 4 different rectangles. That means I'm going to break this up into 4 rectangles, like so. Okay, sorry, I apologize for my drawing ability. But by breaking it up into more rectangles, this should be a little bit more accurate of an estimation than just doing one rectangle, especially if there's a lot of change happening with my function. Well, how would I calculate the areas of each of these rectangles? Well, let's just take my first rectangle. My first rectangle, my height would still be the same. It would still be f of a as the height of my rectangle, but my base would be slightly different. What's this distance? Well, this distance would just be my total width divided into 4 equal pieces. So this would become b minus a divided by 4. That's this width, because it's the difference between a and b divided into 4 pieces. Okay, well that's just the area of this rectangle, so that's rectangle 1. What about rectangle 2? Rectangle 2 has the same exact width. So rectangle 2 still has a width of b minus a over 4. Right? Because I'm breaking it up into 4 equal pieces. I'm breaking up this width into 4 equal pieces. But it does have a different height because my height is dependent on what the function is doing. If I just keep the height the same, then I might as well just do the one rectangle. But in order to make this a more dynamic estimation, my height depends on what the function is doing. That means I need to know what this x value is. Let's go ahead and label this x value x2. Why x2? Because a is technically going to be our x1. So instead of writing f of a, I could write f of x1 here, representing our first important x value. And now our second important x value is x2, and I need to know the function value at x2. So this represents the area of my second rectangle. This was the area of my first rectangle. And I can keep going, right? So then if I call this my x3, my area of my third rectangle would be f of x3 times the width is still the same, b minus a over 4. And then the area of my fourth rectangle would be f of x4 times b minus a over 4. Once I have each of those rectangles, to estimate my total area, what am I going to do? I'm going to add all of these together. And that's how I can estimate the area under this curve more accurately than just doing one rectangle. Well, it turns out because I don't have to limit myself to just 4 rectangles, I can use any number of rectangles to do this. My very technical way to express this is using a Riemann sum. What is a Riemann sum? A Riemann sum is a mathematical way to express whenever I'm summing a lot of values together. So, to summarize what we're talking about, pun not intended, the area under the curve for a function can be approximated by making a whole bunch of rectangles and adding the areas of those rectangles together. So, to show that I'm adding, I use this summation notation. It's a sigma. It's called a sigma notation because that's the capital letter sigma, which is Greek. Okay. And what am I summing up? I'm summing a whole bunch of areas which I got from doing from doing the height of the function, which was f of my corresponding x value. Now, since this x value is changing, I'm going to use an index here using a lowercase I. That I represents an index, and we'll come back to that in a little bit. Times by In our case, it was this b minus a over 4. Well, what is that b minus a over 4? That b minus a over 4 is my width between my x values. I have another way to express that from when we talked about derivatives. I can express that using delta x. Delta x represents that distance between your x values, your change in x. Okay. And in our case, since we broke up into 4 rectangles, this I value went from 1 to 4. So the bottom underneath the sigma is representing the starting point, where are you starting, and above the sigma is where you're going to stop. Since I'm going from 1 to 4, that tells me I'm looking at 4 different x values and calculating the areas for each of those 4 x values. Okay, and what did we see that delta x was? I can calculate delta x by just doing b minus a over 4.
Okay, let's see this concept in action for an actual problem that you might see on your, well, that you will see on your homework. This is coming from your homework. So let's consider this function. F of x is equal to 0.05 x to the 4th power minus 1.21 x squared plus 80. And what we're going to try and solve for is we're going to try to approximate, right? Meaning we're just going to estimate, because this is obviously some sort of curve. We can't figure this out exactly, at least yet. We're going to approximate the area under the curve over the interval 1 to 9. Okay? Which means, what are we going to do? We're going to try and solve, or at least approximate this value. Okay. You'll notice I've used this skinny s notation for area under the curve, just like I used it in 4.1. But these are for 2 very different things. And in our next video, we'll talk about why they're related. Regardless, though, this symbol means we're finding the area under the curve over this interval. But like we said, we're just going to approximate this. We're going to approximate it using 4 subintervals. So just like the example we looked at before. It doesn't have to be 4 subintervals, but it just so happens that we're going to be using 4 subintervals for this one as well. Okay. Well, let's take a look at, if I just write this as a Riemann sum, let's make sure we understand what that would look like. I'm starting at 1 like normal, and what am I going to? Well, since I'm doing 4 subintervals, once again, I'm going to go ahead and go to 4. Okay. How do I get the heights of each of my rectangles? I use the function. I use the function to actually figure out what the heights are, because the heights correspond to what my y values are. Okay. Times delta x represents the width of each rectangle. What's my width of each rectangle going to be? Well, in our case, it's going to be the distance between my x values, my starting x value and my ending x value, divided into those 4 subintervals. So in our case, it's 9 minus 1 divided by 4, which is 8 over 4, which equals 2. Now, like I said, we're not locked in with 4 subintervals. We don't have to use 4 subintervals every time. So if I created a general case here, how would I find this delta x? Well, it's your ending x value minus your starting x value to get that distance between the two, divided by however many subintervals there are. And so we'll use n to represent number of subintervals. Okay. So that's what would be my Riemann sum. But remember, all a Riemann sum means is that we're going to be adding a whole bunch of stuff together. We're going to be adding a whole bunch of these areas together. Each of these terms represent an area. Okay, so let's do this. So my first term is f of x1 times delta x. What's x1 in this case? x1, you'll notice that the problem says use the left endpoint. If I go back to my picture up here, when I made this rectangle, notice which side of the rectangle corresponded to the actual function value. We used the left side of the rectangle we use the function value from the left side of the rectangle to determine the height. So that's what it means by using the left endpoint, is we're going to use the left end of the rectangle, or we're going to use the left point. What that means is for my first rectangle, I'm going to use my starting value. x1 is just your a value, your starting value. So I'm going to use 1. So for this first one, I'm going to do f of 1. x1 is equal to 1 for this specific problem. And what did we say? Delta x, in our case, was just 2. Okay, what about my second rectangle? My second rectangle, to get my height, I need a new x value. What's x2 going to be in this case? Well, x2 is going to be what's my next x value after I go a certain distance? That distance being delta x. Well, in our case, delta x is 2. So if I start at 1, go a distance of 2, what's my next x value? In our case, 3. Okay, because 1 plus 2 is equal to 3. Okay, so that means that's what I'm going to plug into my function in order to get my height times what's my width? My width is still 2. My width will always be 2 for this problem. Well, next, so that's the area of my first rectangle. So this is my first rectangle. There's my second rectangle. My third rectangle. F of, what's my third x value that I'm going to use? Well, I'm going to do something similar. I'm going to just go ahead and add another delta x to my x value to get my next one. If I'm at 3, and I go another delta x, in our case, which is 2, if I go another 2, I end up at the x value of 5. So f of 5, that's my height for this next rectangle, multiplied by my width, which is delta x. That's my third rectangle. And last, since it's 4 subintervals, I should have 4 rectangles. My x4 value is 7, because that's just 5 plus 2. I'm going to add another 2. I'm going to go another 2 distance from my x values, and I get to 7. Times the width is still 2, and there's my 4 rectangles. Now you might be wondering, wait a second, why didn't we use the x value of 9? Why didn't we use 9? It's part of my interval. Shouldn't 9 be one of my x values? But because we use left endpoints, this final rectangle uses the value of the starting x value. It doesn't use the y value for the ending x value. It doesn't actually use this b value at all. So it turns out, because I'm using left endpoints, I never use f of b. But we can see that if I went one more, if I added 2 to 7, I would end up at my endpoint of 9. And so that's how I can tell that I got my 4 rectangles correct. Because each of the distances between these two is between these x values. The distance between each of these x values is 2, which is what our delta x is. Okay, so how do I actually get these values? Okay, well, to get these values, all I'm going to do is I'm going to plug these values in. Okay. When I plug 1 in, I get 78.84. When I plug 3 in, I get 73.16. When I plug 5 in, I get 81. When I plug 7 in, I get 140.76. So I now have my y values for each of those specific x values, which gives me the height of all my rectangles. So now I can multiply each of these values by 2 and add them all together. When I do that, I get 157.68, 146.32, 162, and 281.52. Okay, so just a reminder, right? I found the function value and then multiplied it by 2 because that's my delta x. That's my width of each rectangle. And then I want to add all these things together. When I add them all together, 157.68 plus 146.32 plus 162 plus 281.52, I get 747.52. And that's my approximation for the area under the curve. Okay. Good luck with your homework. Let me know if you have any questions.